Well, Unit 4 is really the heart of this course. It's where we put our understanding of MOS electrostatics and a modern understanding of transport together into a description of modern short channel MOS field effect transistors. So let's recap what we have, the ground that we have covered in Unit 4. These are the learning objectives that we set out with. The first was to understand this modern approach to electron transport, how it simplifies under low biases and high biases, so that we can apply it to the linear and saturation regions of MOSFETs. We talked about ballistic MOSFETs. You should be familiar with how a ballistic MOSFET works and concepts like ballistic injection velocity and ballistic mobility, what those concepts mean. You should understand why the velocity at the virtual source and the drain current saturate in a ballistic MOSFET. You should be able to explain in a MOSFET where there is some scattering what the apparent mobility is and what the injection velocity means. And then you should understand how, with two simple modifications, we can extend our virtual source model so that it accurately describes modern transistors. And finally, you should have some introductory acquaintance with analyzing IV characteristics and extracting some useful understanding of the transport that's going on inside that transistor. Okay, so first topic was this so-called Landauer approach to electron transport. The picture was that our contacts are large, near thermal equilibrium reservoirs of electrons characterized by Fermi levels that may be different. The device connects these two contacts, and it provides a connection between these two reservoirs of electrons. And we didn't derive, but we simply stated the relatively simple current formula. Current was related to some fundamental constants, a parameter we called the transmission, a parameter we called the number of channels or modes, and to the difference in the Fermi functions between the two contacts. And then we sum everything up over all of the energy states that are available. We showed how this general equation simplifies under low bias, and that gives us a way to treat the linear region current of a MOSFET, and under high bias, and that allows us to treat the saturation region of a MOSFET. These parameters in our current equation, the first one was the transmission. Simply a number between 0 and 1 represents the probability that electrons that come in from the source will exit the drain or vice versa. It depends on the length of the channel. The shorter the channel, the easier it is for electrons to get across. It also depends on this parameter lambda, the average distance between backscattering events, which knock the electron around and might cause it to return to the source. Now, we also mentioned that if we use the Einstein relation, we can relate the mobility to the diffusion coefficient. The mobility is easily measured and often measured in something that we typically know. Then we can deduce the diffusion coefficient. Why do we want to deduce the diffusion coefficient? Because there's a very simple relation between the diffusion coefficient and the mean free path for backscattering. This V sub t here is the thermal velocity, lambda is the mean free path. If we deduce the mean free path, then we can compute the transmission, which is an important thing to know. Now, what is this velocity? In thermal equilibrium, the average velocity of electrons is 0. Electrons are bouncing around in random thermal motion and going nowhere on average. But if we take this thermal equilibrium distribution of electrons under non-degenerate conditions and only look at the electrons that have positive velocities, they will have some average positive x-directed velocity. That's what we call the unidirectional thermal velocity. We call that V sub t. It depends on temperature and effective mass. This is an important quantity that appears repeatedly in our analysis of these MOSFETs. Another parameter in the current equation is the number of channels, M of E. And these are like the lanes on a highway that carry the flow of traffic on a highway. Channels carry the flow of electrons in the device. There has to be a state to hold the electron. So the number of channels is proportional to the density of states at that energy. And the state has to have a velocity so the electrons can flow. So it's also proportional to the average x-directed velocity in that state. So transmission channels were two important parameters in this current equation. So this current equation allowed us to have a really simple understanding of how current flows in a small nano device or nano MOSFET. So let's assume that our device is a small chunk of maybe silicon with an energy band that looks like this, E versus K. There are two contacts, one with a Fermi level EF1, that's our source, another with a Fermi level EF2, that's our drain. And I'm showing EF2 a little bit lower because we've applied a small positive voltage to contact 2, the drain. Positive voltage lowers the quasi-Fermi level, or the Fermi level in contact 2. Now, it's easiest for us to understand what's going on under T equals 0 conditions, because then all states below the Fermi level are filled, all states above the Fermi level are empty. So if I look below Fermi level 2, it's also below Fermi level 1. Both states are filled with probability 1. F1 minus F2 is 0. No current flows in any of those states. If we look above Fermi level 1, that's also above Fermi level 2. There's no probability that any of those states are occupied at T equals 0. So F1 minus F2 is 0 minus 0. Also, no current flows in those states. The only states to be concerned about are states between the two Fermi levels. There, F1 does not equal F2. Current will flow. We refer to that as the Fermi window. So let's say we have a state there that happens to be empty. That state is below Fermi level 1. So contact 1 says that state should be filled and sends an electron in to fill it. But then contact 2 looks at that state and says that state is above my Fermi level. That state should be empty. So the electron flows out of that state into contact 2 to empty it. And we get a continual steady state flow of electrons in from contact 1, out to contact 2, which represents a current flowing in contact 2 and out contact 1. That simple picture is how current flows in a small nano device. Differences in Fermi level cause current to flow. Well, the next thing we did was to move on to the ballistic MOSFET and apply that current equation to the linear and to the saturated regions of a ballistic MOSFET. We saw that we could write the linear region current in this way. We could manipulate it so it looked very much like the traditional model with only one change. The one change was that instead of putting the mobility itself in there, the mobility that's determined by scattering in a bulk semiconductor, we introduced a quantity called the ballistic mobility. And it had a well-defined value in a ballistic MOSFET. Under saturation conditions, we could apply our current equation to saturation conditions, and we deduced a current equation that looks very much like the traditional velocity saturation model. It's just that instead of using the high field scattering limited velocity in bulk silicon, we use this unidirectional thermal velocity. Okay, now let's go back. Let's talk about the ballistic mobility first and how it differs from the diffusive or the conventional mobility. So the conventional mobility that we talk about in a bulk semiconductor is related to the mean free path for scattering. This is a material-dependent parameter that is widely measured and usually easy to look up and find. What happens in a ballistic MOSFET? Well, we have strong scattering in the reservoir of electrons at the source. Electrons enter the channel and go about across the channel ballistically and do not scatter at all. After traveling a length L, they enter the second electron reservoir where there's more strong scattering, and they quickly scatter again. So the average distance between scattering events, the mean free path, is the length of the channel itself in a ballistic MOSFET. So the mean free path is the channel length. We just replaced the mean free path in the mobility expression by the channel length, and that gives us the ballistic mobility. So it has a sensible physical interpretation. It turns out we can actually plot at the virtual source the average velocity versus drain to source voltage. And we'll find that the velocity first increases linearly with drain voltage, or with electric field, which is drain to source voltage divided by channel length. But instead of the velocity being the conventional mobility times electric field, the velocity is the ballistic mobility times the electric field. And then the velocity saturates under ballistic conditions at the top of the source, at the virtual source, top of the barrier, and it saturates at this unidirectional thermal velocity, not at the high field scattering limited velocity. So we get velocity saturation with no scattering at all in a ballistic MOSFET at this special point, the virtual source. We talked about the physics of that by showing some numerical simulations of what happens at the virtual source when we increase the drain voltage. If we start out at 0 voltage between the drain and the source, we have an equilibrium distribution, equilibrium Maxwellian distribution of electrons, no average velocity in any given direction. If we apply a small drain voltage, we will lower the Fermi level in the drain, contact 2. That means there's a lower probability that negative velocity states at the top of the barrier can be occupied, and we'll see smaller numbers of negative velocity electrons. The overall average velocity then will increase because we have fewer negative velocity electrons. We increase the drain voltage again, we'll have even fewer negative velocity electrons, and the average velocity will increase more. But if we increase the drain voltage enough, we will cut off all of the negative velocity electrons. We will only have positive velocity electrons. Their average velocity is the unidirectional thermal velocity, and we can't make the velocity at the virtual source any larger than that. These electrons are thermal equilibrium electrons that came in from the source. So that's the physics of velocity saturation in a ballistic MOSFET. Now, in reality, we have to be careful and include Fermi Dirac statistics. We've been avoiding that in most of this course just to keep the mathematics simple and the concepts clear. But in reality, if we want to analyze measured data, we should be more careful about this unidirectional thermal velocity. It actually depends on the location of the Fermi level. So the more electrons that we have in the inversion layer, the higher the Fermi level and the more the thermal velocity. It will start out under non-degenerate conditions at about 1.2 times 10 to the 7th centimeters per second in silicon. But if we go to high densities under on-state conditions, it can be almost a factor of 2 higher. So that's important to know. Well, the next thing that we did is look at adding scattering. Having understood the ballistic MOSFET, we know that most MOSFETs operate in a regime where there is some scattering, not completely in the diffusive limit that was treated by MOSFET models 20, 30, 40 years ago, but somewhere in between the ballistic and diffusive limits. It seems one could guess that the thing to do would be simply to take the ballistic expressions and multiply them by the transmission, the number between 0 and 1, and then we would account for the scattering. That's the correct thing to do under low drain to source bias, but as we discussed, we have to be a little more careful under high bias. Careful because we have to account for the fact that MOS electrostatics demands that we have the same density of mobile electrons per square centimeter at the virtual source, no matter how much scattering is there. And when we account for that, we find that we have to multiply the ballistic saturation current, not by the transmission under ballistic conditions, but the transmission divided by 2 minus transmission. We also mentioned that the transmission under linear region of operation is less than the transmission under the saturated region of operation. And we explain that with energy band diagrams. So under low drain to source bias, if an electron is injected into the channel from the source, if it backscatters anywhere along its path to the drain, it has a chance of returning to the source. So the entire length of the channel is important in determining the transmission. Now, under high drain bias, we're going to give electrons much more energy. They'll scatter more. We might expect the transmission to be lower, but in fact, it's higher. How does that happen? Well, in an energy band diagram, if we look at the bottleneck that's limiting the current flow, the bottleneck is this region near the top of the barrier. Electrons that are injected from the source have to get across this region. If they get across that region, they gain a lot of energy in the strong electric field near the drain. They scatter a lot, but that strong electric field is going to make sure that they get swept out of the drain and can't return to the source. So if an electron can get across that thin region of length script L, which is a tiny fraction, roughly about 10% of the channel length, then the electron is going to go out the drain and the transmission will be high. So for that reason, because the critical length for backscattering is so much shorter, the transmission in practice is higher under saturation conditions than it is under the linear region of operation with low drain to source bias. Now, we also manipulated that. Instead of dealing directly with transmissions, which is not a parameter that is used in conventional MOS theory, we recast those expressions into expressions that look more like traditional MOSFET models. Then we saw a mathematically equivalent expression that we could write the linear region current just like the traditional expression with one difference, an apparent mobility instead of the actual mobility. And we could write the saturation current just like the traditional velocity saturation expression, except that we replace the high field saturation velocity by this quantity we called injection velocity. The apparent mobility is the lower of the actual scattering limited mobility and the ballistic mobility. And remember that the ballistic mobility is proportional to the channel length. So as the channel length gets shorter and shorter, it's the ballistic mobility that's going to dominate. The injection velocity is related to the transmission, and the injection velocity is always less than the unidirectional thermal velocity because the backscattering causes some negative velocity electrons to be apparent there. Well, those two parameters, and they're not empirical parameters that we adjust to fit data, they have a sound physical meaning. With those two parameters, we can take our level 2 virtual source model and we can extend it so that it accurately describes modern short channel MOSFETs. We simply replace the saturation velocity with the injection velocity and the mobility with the apparent mobility, and then our model fits devices well. You know, this is an example of the kind of fit that you can get to modern short channel transistors with just a small number of fitting parameters in this virtual source model. There are a few inputs that we need to know, and then we get some very useful outputs by fitting the measured data. We discussed very briefly how we might analyze measured data and extract some physical parameters like the transmission. So it's easy to show that the transmission is just the measured apparent mobility, which we extract from the data, divided by the ballistic mobility, which we can compute. By doing that analysis, we can extract the transmission. Knowing the transmission, we can extract the mean free path. Knowing the mean free path, we can deduce what the mobility would be in the corresponding long channel MOSFET. Under saturation conditions, the transmission is related to the injection velocity and to the unidirectional thermal velocity, which we can compute. We showed how we can use that analysis to deduce what is the length of this critical bottleneck regime. And we showed that it was about 10% of the channel length for a couple of different transistors. Okay, so let's summarize what we've learned in Unit 4. We developed an understanding of this Landauer approach to transport, which allows us to treat both ballistic and diffusive transport and transport in between those two limits. We discussed the ballistic MOSFET and developed some familiarity with what the IV characteristics of a ballistic MOSFET would look like. The concepts of ballistic injection velocity and ballistic mobility were introduced. We discussed how velocity saturates in a ballistic MOSFET at the virtual source and why the drain current saturates. And then we went on to explain what happens in a realistic device where there is some scattering and how we can introduce these concepts of apparent mobility and injection velocity and what their physical meaning is and how we can use those two parameters to make a very simple extension of our virtual source model so that it provides us with a highly accurate, very simple, very physical model for modern day transistors. And then we took a quick look at some measured data and showed how we can analyze it and extract some useful information about the transport going on inside those transistors. So that wraps up Unit 4, really the heart of this course. But in the next unit, there are some other topics that I want to introduce and things that you should be aware of. Things like the limits of transistors, some different kinds of transistors. So we will discuss those topics in Unit 5.